All right, today we're going to crack open something you've probably seen a million times but maybe never really thought about, the instant cold pack. You know, you squeeze it, you shake it, and suddenly it's ice cold. It feels like magic, right? Well, it's pure science, and it all starts with a very common problem.
So picture this. You're at a game. An athlete goes down. The trainer runs out. They need to get that injury cold and fast to reduce the swelling. But they're on a field. There's no ice bucket, no freezer nearby. What do? This isn't just a medical problem. It's a really cool engineering puzzle.
So, if we're going to invent a solution from scratch, we have to start by setting the rules of the game. What does our perfect solution actually need to do? What are the requirements?
Well, for starters, it has to be portable, right? Something you can just toss in a first aid kit. It also needs to be totally safe, just sitting on a shelf at room temperature for, I don't know, months or even years. And here's the most important part. It has to get cold instantly, on demand, whenever you need it. These are our engineering marching orders.
Now, to engineer something that gets cold, we kind of have to back up and understand what cold even is. And the secret isn't in making cold, it's in understanding heat. The clue is hiding in some basic physics.
Let me ask you a question. Think about a blacksmith pulling a glowing, red-hot piece of metal out of a forge. It's incredibly hot. As it sits there, it cools down and it stops glowing. But all that energy, it doesn't just disappear, right? So where does it go? It's all about something called thermal energy. Basically, the energy of tiny moving particles. And here's the one rule you have to remember. Thermal energy always flows in one direction, from something warmer to something cooler. That's it. So when something cools down, all it really means is that it's losing its thermal energy to whatever is around it.
And that brings us to the big aha moment. We don't put cold into an injury. That's not how it works. To make an injury feel cold, you have to pull the heat out of it. Our cold pack needs to become that cooler object so that all the thermal energy from the body naturally wants to flow right into the pack.
Okay, but how in the world do you make something colder than a person's body, right there on the spot, without a freezer? The answer, my friends, is chemistry, and it turns out some chemical reactions are just perfect for this.
So we're all familiar with reactions that release heat. We call them exothermic. Think about a campfire or one of those little disposable hand warmers. You snap the disc and a chemical reaction starts pumping out heat, making everything around it feel warm. And this is the big question. If we can use chemistry to release heat and create warmth, is it possible to find a reaction that does the complete opposite? A reaction that actively sucks in heat from its surroundings, making everything around it feel cold.
And the answer is a huge yes. You just have to find the right ingredients. Look at this lab data. Some mixtures, like vinegar and steel wool, get warmer. But look at the bottom two. Vinegar and baking soda, that dropped the temperature 4 degrees Celsius. Not bad. But water and ammonium chloride, whoa, that caused a 7-degree drop. That's a serious temperature change. These are our winners. These are the endothermic processes we've been looking for.
So there we have it. We found our chemical engine. Mixing water and ammonium chloride gets really cold, really fast. Now we just have to build the vehicle around it. It's time to actually engineer the pack itself.
The design process for this is actually pretty logical. First, you nail down what the container needs to do. Then you brainstorm what to make it out of. You sketch out a few ideas. And finally, you figure out the most important part. How do you get those two chemicals to mix at the perfect moment?
The design has to solve a few tricky challenges. You've got to keep the water and the chemical powder separate while they're sitting on the shelf. The whole pack needs to be tough enough to get tossed around in a sports bag, but the inner pouch has to be weak enough to break when you squeeze it. It's a classic engineering trade-off. It has to be strong and weak at the exact same time. And that's why most cold packs use that clever bag-within-a-bag design.
So we did it. We solved our athlete's dilemma. But this whole principle of controlling the energy in chemical reactions, it goes so much further than just first aid. Let's just zoom out for a second and look at the big picture.
Okay, so on one end of the scale, we have our simple little cold pack. But on the other, you have these massive, world-changing industrial operations like the Haber-Bosch process. This is the process that makes most of the world's fertilizer. It works by combining nitrogen and hydrogen under incredibly high heat and pressure. Managing all that thermal energy is one of the biggest engineering challenges there is. It's the same science, just on a scale that literally feeds the planet. From cooling down a sprained ankle to feeding billions of people, Understanding how to engineer chemical energy is one of the most powerful tools we have. Which kind of makes you think, doesn't it? Now that you know the basic secret to creating instant hot or cold, what problem would you solve?